everyone, and welcome to the 52nd Surface Ventures keynote webinar. It'd be great for you to say hello in the chat and tell you where you're joining from today. Hi, Michael. Welcome to this event. Joining from Belgium. Great to see. My name is Dr. Sam McMaster, and I'm the content manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class surface and material science education for both academia and industry. Today, it's my pleasure to introduce Dr. Rob Beedwing from the University of Birmingham. Dr. Rob Beedwing is an assistant professor in the School of Engineering at the University of Birmingham. His research concerns tribology, the preclinical assessment of medical devices, and in situ assessment of material degradation. Mechanical joint simulation is a gateway technology for the safe introduction of medical devices, but current standards provide limited actionable data on real-world performance. He has over 20 publications and has received funding from the EPSRC, MSCA, and industry. Many thanks to today's partner, SimSol. Colin Cummins-White, the commercial lead of SimSol, will be joining us later in the event. We'll also be releasing handouts and poll questions from SimSol. So it'd be great if you can answer those and tell us more about your required testing capabilities. Any technical questions concerning SimSol's testing platforms will be taken away and brought to the relevant experts, and answers will be emailed following the event. So for anything specific, please do type those questions in the chat. All questions will be dealt with in the chat, as we have for all of our previous events. So please do type them, and I will mark them for the Q&A session later in the event following both of the talks today. We're planning for around 60 minutes in total, and we'll be sharing a link for your attendance certificates later in the event. Once you have those, please post and tag us on LinkedIn after the event. It's always great to tell your friends and colleagues more about these webinars. So without further ado, let's welcome our speaker, Dr. Rob Beedwing, and proceed with the webinar. Rob, please come on stage.
There we go. That seems to be working. Good morning, everybody. Let me just share my screen.
Great.
Okay, so I think that's working. That should be coming through. All right. So yeah, thank you, Sam. Yes, thank you for that introduction, and thank you to Surface Ventures and for inviting me to speak this morning, and to Simulation Solutions or ProSim for sponsoring the event. So as Sam has said there, my background is in tribology. My PhD and various postdocs before I was appointed a lecturer at Leeds and then moved to the University of Birmingham was in the preclinical testing or the tribology of medical devices. And I also spent some time in industry in some of their R&D test labs. So I've got coming on to 15 years of experience operating and working with mechanical joint simulators. Now, joint simulation is a term that kind of predates a lot of in silico or computer-based modeling. And what we're actually referring to are these large mechanical devices which take clinical components. So some of the earliest examples are clinical hip replacement components, and then simulate them through some kind of articulation profile, usually a simplified gait. So they've been used for as early as the 1960s. The first one that I'm kind of aware of would be the Mark I simulator at Stanmore Hospital. And there were various others around, but they were mostly single station devices until kind of the design and the introduction of multi-station devices, which allow testing of multiple bearings or multiple sets of components at once. And they typically use fairly simplified kinematics or simplified sine waves just to run through a simplified walking cycle, up until the Leeds hip joint simulator in 1980 by Dowson and Jobbins, that then kind of introduced some actual biomechanics or biomechanical profiles that were derived from the literature, which I'll cover in a little bit. So the reason that they're used as preclinical assessment for devices is for a long time the wear of metal on polyethylene bearing, or the polyethylene wear, was a good indicator for kind of a long-term performance of metal on polymer devices. So this started really in the 1950s, 60s with the introduction of Sir John Charnley's low friction arthroplasty. Charnley was actually primarily concerned about the friction of the device, which is why he initially used PTFE or Teflon for the polymer, and insisted on a kind of very low or very small diameter of femoral head in order to reduce the torque transferred kind of through the hip joint. But ultimately, these components wore out way too rapidly, so there was a switch to high molecular weight polyethylene. Ultimately, though, wear kind of became the main focus, or the kind of limiting factor for hip replacements, in the wear debris or the polymer particles that were released from these joints, as you can see in an image here, would agglomerate, would be released in a very specific bioactive range. So they were around submicron, less than 1 micrometer in size, and they would go on to elicit an immune response. I'm not going to go into too much detail around the mechanisms here, but basically your immune system would come across the polyethylene debris, treat it as an invading body, and send out cytokines, inflammation markers like interleukin, tumor necrosis factor alpha, to signal the presence of an infection, and that would go on to elicit other proliferation of osteoclasts. I think that's the right way around. In order to, and the consequence of that is bone resorption. So your own immune system, it's referred to as aseptic loosening, would essentially result in the resorption of bone around an implant, and ultimately cause a loosening of the device. And this, for a long time, was essentially the limiting factor for the survivorship or the success of hip replacements. So I mentioned there was some work done to look at the biomechanics in order to derive the joint contact forces at the hip, and this was referred to as the Paul curve, so as early as 1967, where there was some force plate data that was then transferred through a biomechanical analysis in order to derive a contact profile of the forces that the device is essentially subjected to under articulation. And that typically would mean that you would have, or what that analysis showed is that you would typically have a twin peak loading profile. So you would have an initial heel strike peak load, followed by a toe off load with an intermediate phase, and then a swing phase as your leg then moves through to the next cycle. So it was this Paul curve that was initially applied to on the Dowson simulator, but ultimately this has been simplified or driven by a need to standardize the testing profile, initially into what was referred to as the Leeds Mark II profile, where you had this, again, simplified twin peak profile for heel strike and toe off with a swing phase, and then a collection of sine waves, leading ultimately to the development of the modern standards, where the focus of these standards really is to, as I said, standardize the testing methodology, but in order to determine a benchmark long-term wear rate for a device or for new product introduction. So the ISO 14242 standard concerns hips. There's a 243 standard for knees, the standards for spines. There are standards in development for the shoulder and existing standards for the ankle and spinal disc replacements. But these tests are ultimately really long, really labor intensive, really costly to run, both in terms of consumables, but just the kind of equipment that you have. They run for 5 million cycles at 1 hertz, so continuously, which isn't really representative of how these devices are expected to articulate in vivo. You know, we don't just walk around continuously for an extended period of time. Fetal bovine serum is used as a lubricant, and that's often diluted with deionized water. It doesn't have a lot of the constituent things like lipids, hyaluronic acid that's present in synovial fluid. And mass loss is essentially determined gravimetrically ex situ. So the components are taken off every week, they're cleaned and they're weighed in order to determine a mass loss, and then that's your wear rate. That's your benchmark polymer wear rate to try and assess a change in device design or a change in device material, to basically kind of give an indication of whether or not that is going to be more or less likely to be successful compared to a device that's already has on the market with clinical history and their simulator wear rates essentially. So what we've ended up with is this measure of a benchmark wear rate as a successful standard, and that's driven a lot of the development around metal on polymer hips, mostly from a materials perspective. So from the switch from high molecular weight to ultra high molecular weight polyethylene, the addition of cross-linking in order to prevent delamination, particularly in knees around that, and also antioxidant polymers. But ultimately, the goal here is to quantify that release of polymer debris. And what you end up with is basically running these tests, which for a 5 million cycle test, it will often take 3 months to just run the test, to mind any kind of development or fixture development that needs to be done. And you end up with a fairly basic wear rate at the end of the test. Typically, it can exhibit a kind of bedding in phase, and then a steady state phase, and it's this steady state wear that we're really kind of, what's this steady state wear rate that we're really kind of looking at. But yeah, as I said, that's kind of resulted in the expense that's needed to run these tests in order to get a new product or a new material to market, not really giving you much actionable information on how these devices really are likely to perform. All you can do is compare this benchmark wear rate to some other data that you already have in the lab for an existing device with clinical history. So much of my research and much of the work through my group in the advanced simulation, medical simulation and testing laboratories at the University of Birmingham has been around improving and just making these tests more useful. And that's primarily taken two tracks. The first one we're going to talk about initially, where we're looking at representative inputs. So rather than the simplified kinematics of the ISO profile with just the sine waves, looking at patient-derived profiles in order to accurately represent or replicate what the routines that the devices are expected to undergo in vivo. So we started that by first looking for, developing a modern hip simulator platform. So this was done as part of an EU Framework 7 grant at the University of Leeds in collaboration with ProSim. So we developed a full ISO electromechanical simulator, which you can see kind of swinging around there at the top right. The reason that we went fully electromechanical is previously simulators would typically use either a pneumatic or a hydraulic loading kind of loading system to apply things like axial force. And particularly with pneumatic, that would result in there being a delay or a lag around your desired input force compared to the outputs, and often you would have to go through an additional stage to kind of retune those inputs to provide the output that you needed. But with the fully electromechanical control, we can get a very close agreement to the input profile, and that enables us to do basically a lot of cool stuff around putting in specific patient profiles. So we developed this advanced simulating platform. We actually kind of went through two. So we have a standard plus wear simulator with 3 stations, and then the load soak station for correcting the absorption during wear rates. And this thing is capable of applying, pulsing up to 8 kilonewtons of axial force, 60 degrees of flexion extension, adduction, adduction, and then also applying medial lateral force, which becomes important when you start looking at the actual force vectors that are involved in joint contact forces. The second platform was called a universal joint simulator. So this platform is capable of doing hips, knees, and spines initially, but also has this custom designed ring load cell where you can drop in a full stem system. So rather than just looking at the bearing wear or the bearing surface, you can test the device holistically. So you can put the full implant construct into the simulator. So then another part of that project was we essentially went to look at getting the joint contact forces to create the profiles that we needed to run on these simulators. So we worked in collaboration with Chapel Allerton Hospital in Leeds and their gait analysis lab to recruit a cohort of basically 150 plus at this point hip replacement patients. So these were patients with THRs in, and send them through the motion capture analysis facilities at that lab. So that kind of enabled us to derive the representative kinematics, not just for individual patients, but also across demographics. So we can take age, gender, BMI, or even different activity metrics, and I'll explain what I mean by that in a second, and come out with average or representative profiles for kind of those demographics to then put in the simulators. What we mean by activity metrics is when we actually started looking at the data, what we found is that just things like age or BMI weren't necessarily good indications of function or activity in patients, and actually things more akin to cycle time or accelerations were better metrics. So we can start to tease that data out as well. That motion capture was then fed through Anybody multi-skeletal multi-body modeling software in order to determine the joint contact forces. So we have quite a nice suite of different profiles and different trials that we can now load onto these simulators and subject devices to actual, patient-specific or demographic-specific loading scenarios. The model went through a bit of a refinement phase just to ensure that we were getting something accurate. So we calibrated that model against the Bergman orthoload data set in order to make sure that what we found was it was particularly sensitive to things like muscle attachment points and the setup. But what we came to find was a fairly close agreement for the Bergman inputs in order to get the Bergman outputs there. And one of the first things we looked at was looking at BMI. So compared to the ISO profile, we split the patient demographics into healthy weight, overweight, and obese patients, and we ran a hip simulator test, which I'll get to the data in a second. But we ran a hip sim test in order to compare these two different profiles. But you can see, compared to the ISO walking profile with the standard twin peak, and then basically a set of sine waves for the rotation axes, the loads are very different. Loads are lower, typically for a start, even for the obese patient, than the 3 kilonewton peak called for on the ISO profile, and the kinematics are very different. When you look at those kinematics and you compare them to the kind of motion profiles that you expect the contact patch to go over on the hip replacement components, the kinematics are also very different. So the sliding distance is different, the sliding location is different. You don't have this kind of nice oval, but you actually have a bit of an abrupt stop and reverse, and then the areas for peak load and directions of sliding are all kind of very different. So I have a video here just to demonstrate that. And what this video is going to show you is it's going to show you the simulator running through 10 cycles of the ISO walking profile, and then 10 cycles of the healthy weight physiological gait. So I'll just get that started. And what you'll hopefully hear is, so this is the ISO profile, just those sine waves. Sounds kind of fairly sedate, but when we switch to the physiological kinematics, it's just much more abrupt in that turn. The loading is very different. The kinematics are very different, and that translates into the wear rates. So when we compare the wear rates to an ISO profile, so this is the ISO data that I presented earlier on that slide. So we had this bending in phase, and then a steady state wear rate. What we noticed with the BMI data was for all that the loads on both were ultimately lower, there wasn't this clear bending in phase, and actually we just started off with a much higher steady state wear rate. So after 5 million cycles, the wear was higher for the physiological gait, which is the key point to take away from that is, despite the loads were lower, the wear was higher. Typically, it's kind of common accepted knowledge in hip simulation is when you increase that axial load, you'll typically increase wear as well. By introducing the kinematics, we actually brought that axial force down, but still had an overall resulting higher wear rate once we had fully determined that we were in steady state. And then we saw slight differences between the healthy weight and the obese profile. Moving slightly away from wear rate as well, when we actually map the surface damage or the wear patch across the surface, what we see is a change into more a more lateral wear patch. So that because we introduced a medial lateral force to match the kinematics, that resulted in more of a superolateral kind of wear pattern, which has been noted clinically compared to the ISO profile. Another test that we've been able to affect is a jog. So this was from some of, I think only 4 or 5 patients were subjected to a jogging trial. So it's a lower N on the cohort, but essentially we can run these simulators through much more severe contact. So we'll touch a little bit on some of the adverse loading profiles that are typically seen in the literature, but we can introduce stop to start. And one of the nice things that this kind of highlights is that actually with the capability of these simulators, what we can start to do is iterate through profiles. So rather than just running a continuous 1 Hz cycle that repeats over and over again, we can build up activity profiles that then simulate a day in the life of a patient or day in the life of a specific patient population. And one of the things we did, so I said we looked at jogging and also stair negotiation. So we ran one multi-phase test where we started initially just with the ISO profile, and then we switched to a jogging profile, and then which was run continuously, and then switched to jog and dwell, so the jog profile doubled the wear rate compared to the ISO profile over the first 2 million cycles. The dwell didn't increase the wear rate any. We kind of expected it did, but for the metal on polymer device, it didn't, and that may be more important for hard-on-hard bearings. But there was an increase in the kind of variability between the samples there. We also looked at stair descent and stair ascent for only 500,000 cycles each, but the takeaway message there is stair ascent is typically thought or considered to be more of a severe profile, just because of the deep flexion and leverage that's involved in climbing stairs. But actually, we found that the stair descent was more important, and that's likely just because one of the other advantages of the simulators is they're all instrumented with 6-axis load cells, so we can resolve the torques at the bearing surface, and the stair down had this much higher peak in resultant torque compared to the stair up. When we look at just the ISO versus the jog cycle, we can see a much higher single peak in resultant torque compared to then a lower peak versus the ISO, and ultimately a lower swing phase, but this higher single peak in torque resulted in that increase in wear rate that we observed. So there's a bit of a problem coming down the line here, in that these simulator tests, just in running an ISO walking profile, already take an extended period of time, 3 months to run. So when you're talking about simulating different patient demographics, different activity profiles, it's just exploding the matrix of testing that you may be asked to do. There's a little bit of this already going on, in that the FDA are starting to ask companies for more comprehensive testing and adverse loading. We've done some work on jogging for some companies recently. But another package of work that we're looking at is, basically, we're involved in one of the UK Centres of Excellence in regulatory science, the in silico one that's being operated out of Manchester by Professor Alex Frangi, looking at using in silico evidence and what the barriers are in order to have that evidence treated seriously for regulatory approval for these devices. Don't think you'll ever get to the point where a device is fully approved, or the evidence is fully sufficient to approve a device purely off computational modeling. But what we are looking at is shifting to more of a kind of risk-based framework where we can simulate in silico through a digital population or digital twins, and then look at key factors which we might then need to do the mechanical testing. So using it as a tool to inform smarter testing rather than just kind of a blanket approach. So the second stream of what we've done is basically try to get more appropriate outcome measures than just polymer wear from these simulators. So trying to simulate appropriate or observed clinical failure modes beyond polymer wear. We have, we've looked at retrievals and an extended number of implant retrievals where the devices have been removed for wear, but actually the bearing surface doesn't look that damaged. Or we've had devices where the reason for revision was not wear, but when you actually look at the component, then there is significant amount of damage there. So there's a tenuous kind of link there between the clinically reported outcomes and what the device actually looks like. And also in the switch to these antioxidant and harder polymers, where the wear rate has been driven down, there's work that's starting to come out of the States, which hasn't quite been published yet, but I've seen it presented at a conference, where you essentially have non-detectable wear on these new polymers, but you're still seeing osteolytic failure in tissue analysis. And the academics over there describe it as a cloud of almost undetectable polymer debris existing in the joint space. So the wear rate has fallen down, but we're still seeing that kind of osteolytic aseptic loosening driven failure mechanisms. Also, polymer wear isn't necessarily appropriate to all bearing surfaces. So one example of this is the metal on metal kind of product recall that happened in the early 2000s, where there were devices that were switched away from metal on polymer to a metal on metal design, both traditional total hip replacements, but also resurfacing devices, basically driven or kind of brought to market on the back of a much lower perceived wear rate in preclinical testing. But there was rapid downturn in their use because there were essentially other failure mechanisms that were occurring there. So we started to see adverse reactions to metal debris, pseudotumors, metal sensitivity and pain, and then basically the vast majority of these devices have now been removed from market. Some had failure rates as high as, I think, approaching a third, 30% at 5 or 6 years. So polymer wear, or just benchmark wear rate from simulators, weren't a very good metric for their or predictor for their success. So in the aftermath of that, there was a lot of focus on so-called adverse loading profiles in order to try and explain that failure. So there were mostly two that kind of came to the fore that have then kind of fed into the standard. So the ISO 14242 Part 4 standard is now about implant positioning in terms of inclination, and then also microseparation. So for microsep, would either be caused by something like joint laxity or migration of components, is where during the swing phase of a cycle, you essentially have the components separate, and then on heel strike, they come back together and result in an impact or a collision across the bearing surface, and then higher wear. Or acetabular inclination, where just malpositioning of the cup or migration of the cup results in compromise of the lubricating film that generates as a result of articulation in these devices. So some of the work in the literature has found as much as a 2.6-fold increase on some of these things, significantly higher cobalt and chromium ions reported in I think this was in blood ion levels as a result of these devices. So the wear isn't necessarily the be-all and end-all of the metric that's important for how these bearings perform. So one of the branches that we've looked is instrumenting simulators with a 3-electrode electrochemical cell. And this allows you during articulation to kind of measure and extract information around the corrosion of those devices. So this was the bulk of the focus of my PhD, looking at metal-on-metal bearings. So we use a potentiostat, which is essentially a fancy voltmeter and ammeter, in order to connect to the metallic surfaces, and then as sliding happens, as you depassivate that metallic alloy, the oxide film, then interrupts it, and corrosion happens. You can draw direct measures for the corrosion that's taking place. So you can use various electrochemical techniques. In particular here, DC electrochemistry, so you can look at the open circuit potential, just gives you a qualitative assessment of what happens to the kinetics of the reactions that are taking place at the bearing surface. You can use the DC techniques like LPR to get a direct measure of corrosion current or anodic polarization to look and track the corrosive degradation, that anodic current as a result of sliding and depassivation. And one of the things that I did during my PhD was try and link that degradation, that corrosive degradation at the bearing surface, to the lubrication of the device. So what I did was I did some fairly simple tests where I just varied the speed, the frequency of sliding in order to adjust or change the lubricating, the entrainment and the generating lubricating film, and found a fairly close correlation between the anodic current that I was measuring from the bearing and that predicted film thickness. What was interesting around this is a lot of the existing kind of triber corrosion models at the time would predict that as your sliding speed trended to zero, your corrosive degradation would also trend to zero, because if you're not sliding, you're not depassivating. But what we found is that actually the inverse was true, in that when you kind of trended to zero, or when you slowed down in terms of sliding speed, you actually compromised the fluid film more than anything else, and then that resulted in greater corrosion and peaks in corrosion current. So there was a bit of an upending of what we believed there. The other thing was microseparation. So I took a look at the effects of microseparation, both for metal on metal and metal on ceramic devices. And what we noticed is so these were specifically 28 millimeter bearing devices, and we had some existing data in the literature to compare to, which kind of showed a twofold, I think, increase in wear rate when you introduce microseparation. What we actually saw was an order of magnitude increase for metal on metal in the corrosive degradation, or the estimated material degradation, material loss as a result of corrosion from that bearing surface. So there was a shift from around, for metal and ceramic, for around 4% to as high as 17%. So there's a change in the degradation mechanisms there that's occurring, that's not just a bulk wear rate, but important to how material is degrading and leaving the bearing surface, and then ultimately resulting in ions being released into the joint. Also looked at the acetabular inclination. Again, no surprise, increasing inclination kind of resulted in increases in the corrosion current that we were measuring. But what was interesting was that when I changed how you increase the level of inclination from 30 to 50 degrees, whether you ran them in parallel or in series, when you come back down to 30 degrees after a high level of inclination, the corrosion currents were higher at that 30-degree angle than previously. So what that kind of suggested was that when you change your articulation path, or when you change the profile, you change the area of the surface that you're depassivating, the resultant degradation is higher going forward. So that kind of speaks to the importance of switching profiles and looking at kind of daily living routines or day in the life of the patient when you're doing this, to get a full idea of the degradation that's occurring, as opposed to just articulating over a single profile. I kind of skipped through this one because there's a lot of electrochemical data here, just in the interest of time. But not just at the bearing surface, but another concern that's still present is modular tapers. So these are referred to as Morse tapers. They're described as basically a cone-on-cone interference fit, whereas a traditional Morse taper is used for cutting tools on lathes and mills and things. And they're typically long and smooth. They have a shallow matched cone angle. And they're also typically press fit on, which is completely different to how, and they're used to transfer axial torque or force through the tool. It's completely different to how these things are used, or how these things compare to, well, how modular tapers are used in hip replacements, in that you typically have mismatched cone angles, shallow, short threads, and also subjected to complex biomechanical loading. So these things add another interface. They introduce a crevice corrosion interface and produce wear and degradation that way. But one of the things that we wanted to check was, or wanted to look into, was how these devices move up and down the taper, or how they migrate on the taper, and what levels of micromotion and fretting contact, or what kind of fretting contact is present in the bearing there, or in the taper. So we instrumented a simple adapter system with a custom 4-coil eddy current principle displacement measurement kind of ring, which sits underneath the taper, and then also used the 3-electrode electrochemistry to quantify the corrosive degradation. And what we were interested in was basically comparing what is basically in industry standard at this point in a proximal engagement. So most tapers will be proximally engaged, compared to something more akin to a traditional Morse taper, or even a distal engagement. And we did this by varying the taper angle of the male trunnion, and then just used fairly standard heads. But you have this industry standard proximal engagement, smooth tapers or rough tapers. The surface finish was targeted to be indicative of essentially commercially available products, whether it's smooth or referred to as a threaded one. I'll skip through this, but the take-home message was these tapers were described as self-centering, in that a surgeon can essentially knock a head on a modular taper, and it'll be fine. It'll just work. It'll work itself out. But what we found was that actually under uniaxial loading, so I didn't mention we did this under uniaxial, but also under the ISO profile. Under uniaxial versus the ISO profile, so complex gate biomechanics, we found very different types and different levels of micromotion at the taper, and that resulted in different corrosion or different levels of measured corrosion as well. So for uniaxial, it was largely a pistoning motion and subsidence, where for the smooth taper, it basically sat relatively still until you reached a certain load, and then it slipped and migrated down the taper. Whereas for the rough tapers, there was this progressive subsidence going down. And then the proximal taper, which again is kind of industry standard, that's driven by the design requirements for having a ceramic femoral head to make sure that you don't result in burst fracture, basically demonstrated a higher level of measured corrosion currents, high level of pistoning, sorry. That was also true, just moving to the simulated gate, we saw similar things for the smooth tapers, but for the rough tapers, actually what we saw was the head migrate up the taper as opposed to down, and then also an increased level of XZ subsidence. So the axis of the head was actually sat on. So as a result of this biomechanics, you were seeing a change in how the head was basically toggled or arranged onto the device. And then, yeah, as I said, the proximal taper and match tapers basically demonstrated much higher or higher corrosion currents than the distal tapers. But this is typically what is put in vivo, as I said, driven by that need for ceramic heads. So we treat the simulators as platforms. As long as you can fixture devices in, then you can get them in there, and you can subject them to the loading or complex biomechanics that you want. So this was some work that we did around bilateral spinal instrumentation on the universal joint simulator. So again, subjecting these devices to what is basically standardized testing in uniaxial loading versus applying actual complex biomechanics to what you would then see as a degradation response. So what we found is essentially, yeah, this was a set of testing where we sequentially increased or sequentially ran through different profiles by introducing different axes of rotation. And then once you get to the point where you're actually simulating the complex biomechanics, you see an increase, a significant increase in the amount of corrosive degradation there. Just wrapping up, so a project that we have ongoing is looking at total shoulder replacement. So TSRs, they're rapidly exploding, particularly in the United States. I'm not entirely convinced that the clinical evidence or the preclinical evidence is there for their success. And there are standards that are basically in development at the moment, looking at anatomical wear standards and a separate loosening standard in development. But when you look at the kind of registry reported data, common failure modes for these things are just reported as loosening as opposed to wear. There is a bit of wear indicated there, but actually what we're looking to develop is a combined test methodology where we can integrate all of this together. So looking at applying the complex biomechanics, the kind of ASTM F2028 rocking test for assessing primary versus secondary fixation. And one of the things that we're doing is working with some of the team down at the Royal Orthopaedic Hospital to look at this testing to try and help and inform rehabilitation protocols. So how far and how quickly can the physios take patients after shoulder replacement surgery in order to ensure that kind of primary versus secondary fixation and the long-term success of the device. I'll wrap up there by again just mentioning that all of this is kind of dictated by clinically reported outcomes. Really, we want to be testing and assessing devices that kind of match in a way that matches or correlates with the failures that we're seeing. So one of the things, we're quite lucky in Birmingham to have the Royal Orthopaedic Hospital just down the road, who are a recognised national centre of excellence in joint replacement surgery. Their catchment area for revisions is about 8 times the national average. So an initiative we set up is the Birmingham Implant Retrieval Centre, in order to basically collect and harvest all of the metal work, all of the joint replacement surgeries that we can get our hands on coming out of there, so we can send it through the patients, and then rather than those implants just going in the bin, they come to us for engineering analysis, and so then we can start to look at things like early safety alerts for devices if we're starting to see failure mechanisms there, but also use that to inform the preclinical testing. So I'll wrap up there just by saying thank you for your attention, everybody, and yeah, been a pleasure. I think we're getting sound back.
There we go. Sorry about that, Rob. Thank you very much for that great talk. That was fascinating. I do have some questions, but we're going to switch to Colin for a few minutes. So just want to highlight for those in the audience, if you have any questions for Rob, please type those into the chat, and we'll be addressing them in the Q&A after Colin's talk. So for now, Colin, would you like to join us on stage, please? And I will bring your slides up. Perfect. There we go. Okay. Is that all clear? Excellent. Stage is over to you.
Thank you. Good day, everyone. My name is Colin Cummins-White. I'm the Commercial Business Unit Leader for ProSim. part of the Simulation Solutions Group. Today I'm going to give you a short overview of how hip and knee wear simulators have evolved and how that evolution has been driven by changes in implant design, testing expectations and standards. I'll also touch on ProSim's role in the development of early research-focused machines through the modern standards compliance system. To put wear simulation into context, it's worth briefly looking at how hip and knee arthroplasty developed. The first hip replacement was performed by Austin Moore in 1940, but it was really Charlie's work in the late 1960s that established total hip arthroplasty as a reliable, repeatable procedure. In knees, the first total knee arthroplasty came later in 1974 with the work with Ranawat and Walker. These advances created a clear need to understand long-term wear behavior, particularly as joint mechanics became more complex. What's interesting is that the implant development moved much faster than testing standards. For many years, implants were being designed and implemented clinically before there was a well-defined international standard for wear testing. As a result, early simulator work was driven more by research need than by regulatory requirements. This is where ProSim comes into the picture early on. The focus wasn't strictly compliance, but developing machines that could realistically reproduce joint motion and loading, even in the absence of a formal standard. As we go through the simulator generations, you'll see a clear progression. Greater control, accuracy, more test stations, higher throughput, and eventually full alignment with ISO standards and regulatory expectations. Simulator 1 dates back to 1993 and was a redesign of the original Thackeray hip simulator. It enabled hip wear testing at a time when no ISO standard existed, and it effectively marked ProSim's entry into the simulator development market. Simulator 2 followed in 1998. This was a 6-station pneumatic knee simulator developed for Professor John Fisher at University of Leeds. It supported the growing demand for knee wear research and highlighted the need for multi-station repeatable testing platforms. In 2008, Simulator 3 represented a significant step forward. This was a multi-station electromechanical knee simulator capable of running up to 8 tests simultaneously. It allowed testing beyond the ISO requirements, which was important for both advanced research and commercial development. A key change here was the move from pneumatic to electrical mechanical actuation, which brought much better control fidelity and repeatability. Simulator 4, introduced in 2010, was designed with standard compliance as the main priority. It's a 6-station electrical mechanical system for hip and spine testing, built to be strictly compliant with ISO 142421 and ISO 18192-1. This shift reflects the increased importance of generating reliable, regulatory-ready wear data for formal submission. Simulator 5 represents an ongoing evolution rather than a single redesign. It incorporates new generations of control electronics, higher resolutions and sensor data capture, and automation of force and precision demand following. Manual motor tuning has largely been replaced with automated processes, improving efficiency and consistency. The system also supports the latest ISO draft standards with real-time measurement and display of tolerances. All of this fits into the continued development cycle. In silico modeling informs in vitro testing, which then supports in vivo clinical evaluation, where simulators sit at the center of this process, translating theoretical modeling into measurable, clinical relevant performance data. To summarize, where simulators have evolved from research tools into highly controlled, standard-driven test systems. ProSims developed a history that close mirrored that progress, from early compatible driven machines to scalable, compliant, and increasingly intelligent platforms. And the evolution continues as implant designs, materials, and testing expectations advance. Thank you for allowing me to share this short message with you.
Okay. Thank you very much, Colin. So I think now is a good point where we can move to our Q&A. We've got a couple of questions in the chat, so let's welcome Rob back on stage. Fantastic. There we go. Colin, if you do want to join us, perhaps there may be some questions you want to answer, but do feel free to stay off stage if you would prefer. So.
No worries. I pushed the wrong button.
That's okay. Not a problem. Okay, so just for everyone in the audience, I'm now releasing the attendance certificate link, so that should appear in the bottom left. And just want to draw everyone's attention to all the poll questions that are available. If you haven't answered those, please do go ahead and take a look at those. And also take a look at ProSims handout in the Handouts tab. Our first question is from Victor, who says, "Hi Rob, great talk. Based on the increased use of joint replacements in young patients, have you considered the application of other more sport-related profiles beyond jogging?"
Yeah, so we have, and it becomes a bit of a balancing act between, as I kind of mentioned, what you can essentially affect within a time from it, and the expense and the length of time that it takes to run these tests. One of the things we do is whenever we're writing a grant to kind of push this work, is we always build in PPIE activity, so patient engagement, in order to discuss with them, what their everyday challenges are with devices that they have put in, and what they kind of run through day to day. I think there's probably a limit on what you could do. I know that for example, some of the early marketing around metal on metal hips had a ballerina who was involved in the profiles that she was subjecting that hip to. But yeah, I think there's probably limits to what you can achieve. One of the things that we do, or that I touched on with the shoulder replacement, working with the guys down at ROH, is using the rehabilitation protocols that they subject the patients to in order to inform the testing and see where you can push that level of engagement.
Okay, thanks, Rob. And yeah, as you can see, Victor's thumbs up for the answer.
Yeah, I'm sure it'd be useful to kind of do football or whatever people are up to on a weekend, but yeah.
Yeah. Our next question comes from Dirk, who asks, whereas the presented work goes towards making the simulators more realistic, do you also have experience with simplifying solutions or pre-screening methods for materials? I'm referring to work by Professor Fisa, for instance.
Yeah, is that Days of Psycho you're referring to? Yeah, I'm familiar with this stuff. Not in terms of the simulator. So when we're doing simulator tests, we would typically treat the ISO standards as a simplified baseline. We do have extensive work, which I didn't present today because it wasn't really the focus, but looking at material screening, just using simplified 2D or simplified pin-on-plate tribometers and that kind of thing. You can get some kind of initial rapid and interesting information from that. But I think a lot of the time the outcomes of that aren't kind of directly comparable once you then scale up to full 3D testing. So we definitely do some of that in terms of pin-on-plate tribology tests for material screening. But if we're using the simulators, we would treat the ISO standards as a baseline and then push beyond those.
Okay, thank you. Out of curiosity, just for my own interest, would this typically be larger scale tribology test, or would it be more towards the threatening regime, or would it depend on exactly, what kind of activity?
It depends on the interface you're looking at. I mean, for the hip simulators or the knee simulators, typically you're just looking at that bearing wear. But the design of those simulators and protocols are really only focused on that. So that's one of the nice things about the universal simulator, in that you can put in whole construct devices and you can look at the combination and degradation across those different interfaces. So a hip replacement, a typical modern hip replacement, will have the bearing surface, it will have fretting contacts at the acetabular cup shell liner, it'll have a fretting contact at the modular head, there might be secondary tapers, there'll be the stem cement or stem tissue interfaces. It depends. Usually they're only looking at that bearing surface wear, but that's kind of where we want to move towards in full device screening.
Got it. Dirk said that they have to go, but thank you for the nice presentation. And it also says, thank you. It's a matter of cost, of course.
Yeah.
But, yeah. Naturally. Our next question comes from Jacob, who says, great talk. Thank you, Rob. How much impact does the lack of lipids, representative proteins in the choice of lubricant have compared to appropriate solution pH and facilitating ease of onward analysis?
Yeah, I think it's significant, and it's a problem. It's a problem that I'm aware of a number of projects that are trying to grapple with, because it's not just the lipids and hyaluronic acid and things in terms of the tribology at the interfaces, but also just the I mean, you touched on it there, the measures of pH. A diseased joint will have a very different makeup from a healthy joint in terms of pH and the release of peroxides and things. There's the salt content in synovial fluid. When we do tests, we typically dilute with PBS as opposed to just deionized water to try and match the conductivity or there are other standards with sodium chloride for osmolality, but it is significant. And the typical design of these simulators is you have the joint space fully flooded with lubricant, so you need a large quantity of it. So there are projects, and I'm aware of a few other kind of artificial simulated lubricants that have been developed, like the work from Jan Brandt from a while ago, and a couple of other projects that are going on to look at tackling that. We've only ever used bovine serum or calf serum for the majority of our stuff. So the onward analysis one, I'm not entirely sure about, but yeah, just dealing with the calf serum is significant, because that is also a growth media, and we keep it in pots for weeks on end at 37 degrees, and we have to add things like sodium azide and I think the Brandt solution was antibiotics, which then, in order to prevent bacterial growth, but then that then changes the chemical makeup of the serum. Yeah, it's an interesting problem that I've not done any work specifically myself, but I'm aware of some interest in that area.
Yeah, certainly. A very complex problem indeed. Just whilst we're coming to about 6 minutes left of our allotted 60 minutes, so I just want to check for any other questions from the audience. So please do get typing if there's something else you'd like to ask. What I'd like to sort of ask about, Rob, since we sort of Colin touched on the the evolution of the hip simulators, and you'd sort of spoken about the universal simulators. Is that the sort of future trend for your work, being able to basically fully map different patient gaits? You can explore then very specific movement profiles. Is there something else that that's really the sort of objective that you need to get to?
No, I think it is. I mean, a lot of our work is around improving these test methodologies around these platforms. Mm-hmm. One thing that I didn't touch on, because it's part of a grant application, but if it comes off, we'll be acquiring one of those 3-station universal simulators in order to look at the ankle joint. There is a standard, as I think I mentioned at the start, there is an ankle wear standard, but actually loosening and primary fixation is probably one of the bigger concerns around ankle replacements, as opposed to just simulating wear, because you've got complex geometry with the different bony anatomy around the device, and bone and bone ingrowth responds to stress. One of the first things that they do when they have a put an ankle replacement in is they actually immobilize the patient as well. So similar to what we're looking at with the shoulder profiles and assessing that primary versus secondary fixation, we're going to be, if the grant comes off, we're going to be looking at those devices basically from that perspective, but again, using those universal joint simulator platforms.
It'll be very interesting to see. I hope you get it.
Yeah, me too.
Yeah. With the since you talked about loosening a little bit, partially for the you talked about it for the total shoulder replacement, and now for ankle, and touched on it earlier for the total hip replacements. Is the mechanism for all of these these different joints, these different locations of the body, is the loosening mechanism similar for all of them, or are there some differences?
No, it's different. So I mean, yeah, that was what I was touching on with this primary versus secondary fixation of a device. So the hip replacement will go in. It'll be usually fairly secure, whether it's cemented in or whether it's a cementless system. And then loosening in that instance is typically this long-term osteolytic response to wear debris. Whereas if you're looking at devices like the shoulder or the ankle or some of the large kind of mega prostheses, the endoprosthesis replacements that we're doing some work with ROH on around cancer reconstruction. The fixation is the kind of primary fixation is what we'd qualify as immediately after surgery, and then secondary is that long-term kind of fixation of the device once you have some bony ingrowth. In that instance, particularly for the ankle, we suspect for the shoulder, it's more about the transfer or the transfer of torques from the bearing surface that results in that kind of basically results at force or micromotion or movement at that implant tissue interface, whether it's cemented or not. And that's kind of what I was a little bit touching on, with the shoulder work. So the evidence of just purely looking at wear across these devices, which is kind of built up from that legacy of hip devices, pre-screening and hip devices, is probably not appropriate to the clinical outcomes and the difference in how these implants migrate or loosen depending on the arrangement.
Okay, got a. We'll take this as the final question from Mike Bryant, who we all know well. So, where is seen as a solved problem in the ortho industry? Is there a need to redefine the narrative in the field to tribologically associated failures?
Yeah, I think so, and that kind of touches on what I was just saying. In that, where is seen as a solved problem, but then also recently I was speaking to an industrial contact who said that when they change a material in a hip replacement or something, they're expected to do upwards of seven of these ISO 14242 tests. So that's a significant cost, a significant expense. And if wear was a solved problem, that I don't see how that is still necessary. So I don't think wear is a solved problem. It's certainly perceived or talked about as a solved problem in the industry, but I don't think it is. But yeah, a lot of the work that we've been doing has been trying to move these testing platforms away from just a benchmark wear rate in order to look at clinically representative failure modes, which then is what we're looking to extract from the retrieval center.
Okay, great. Thank you very much, Rob. I think now with our time, that's a good point to draw the event to a close. So I just want to say, Rob, thank you very much for your fantastic presentation and discussion of all the questions today. Thank you to everyone in the audience for being here, for asking such great questions. Thank you to Colin for your presentation, the overview of SimSol. And thank you to SimSol as well for partnering with us for this event. We wouldn't be able to do what we do without our partners. So thank you very much. With that, just some final words from me. As a reminder, do take a look on the Surface Ventures website. You can see our archive of previous events on there. The replay for this event will be up in the next couple of days. So if you have a colleague who has missed this and you think may be interested, do direct them there. Do also take a look on our LinkedIn page. Stay tuned to our email emails, and we will keep you updated for our next keynote when it is available. And also, just to say, do advertise these events to colleagues and anyone who will be interested. So with that, thank you all very much. Thank you, Rob. Thank you, Colin. Thanks to everyone in the audience.
Thank you.
Thanks. Bye all.
Thank you. Bye, everyone.